Hello again, everyone, and welcome to Lecture 7 of Environmental Sciences 347, Climatology. This time we move ahead toward atmospheric circulation and regional climates. Specifically about atmospheric circulation today, we're going to dive into the Norwegian Cyclone Model, which was developed about 100 years ago by a group of meteorologists, of course, in Norway, that basically is what we still use today. It involves lows, highs, and frontal features, and we'll get more into that within the lecture. To re-emphasize, next week, the week of March 15th, we'll have the first exam. It will cover lectures 1 through 6. We'll post it on Monday morning. It will be open for 48 hours. You'll have 60 minutes to take it. There will be 40 questions. They will all be multiple choice. So it gives you a little bit more than 1 minute per question. Again, it'll be open for 48 hours. You can take it once, and 40 questions over the course of 60 minutes. So, back to the subject matter at hand. What role does the atmospheric circulation play in shaping the climate regions of the world? Let's go back and review air masses, which we touched on with the last lecture. A huge expanse of air covering thousands of square kilometers, square miles, whatever. But they're relatively uniform horizontally in temperature and humidity. And the properties of this depend on the type of region in which the air mass originates. These basically go as to cold and dry, and cold and warm, dry, or humid. With those four basic types we talked about before: cold and dry, cold and humid, warm and dry, warm and humid. That fifth type, Arctic, is so cold and so dry you don't need to call it continental polar. You just call it Arctic because it is that cold and that dry. The dry is kind of assumed because when the air is very, very cold, read Arctic, there's not that much water vapor in it at all. So you're not going to have an Arctic humid air mass. So in terms of where the source regions are for North America, continental tropical, think dry and hot. That's going to be over the subtropical deserts of Mexico and the southwestern U.S. Think New Mexico, Arizona, and interior California. Maritime tropical is what we think about here in Virginia in July. You know, it is warm and it's humid. It is warm, it is humid, it is warm, and it is humid. The source of this is tropical in geography, and what we also think of, at least intuitively, about tropical and moisture. Remember, when we talk about tropical air mass in this context, in this class, we're talking about the location, not necessarily the humidity level. All right. So maritime tropical is a warm and humid air mass. A continental tropical is a dry and warm air mass. The maritime polar air that develops in the colder waters of the North Atlantic or the North Pacific. Continental polar air, that's basically over the interior of North America. Think about Minnesota, the Dakotas, the prairies of Canada in January and February. That cold, dry air flushing itself into the lower parts of the United States, or the central and southern parts of the United States. Arctic air is just that brutally, brutally cold air that forms up toward the Arctic Circle, Greenland, Siberia, really far north. So here's another graphical schematic about where those air masses originate from. We don't get a lot of true continental tropical air masses here in North America because we don't have that much room. You know, we've got a lot more room to develop a maritime tropical air mass. We've got the Caribbean, we've got the Gulf, we've got the Pacific. Got a lot of room for continental polar air mass, most of northern and central North America during the winter. Then, of course, once you start developing snow on the ground for the winter, by December and January, across most of central and western Canada, that's a fantastic source region for continental polar air masses. And again, when we talk about Arctic, that's way, way north, literally north of the Arctic Circle. So these are the locations where those air masses tend to set up. And you can see from the bottom there, the regions of North America occupied by various air mass types. So this shows you the dominant type of air mass in place. Continental tropical air mass does not take up a lot of square miles in the United States. That's mostly the high plains of Texas, and then heading to the lee side of the Rockies southward from Colorado. Maritime tropical, think about that in the southeast where we are. That's kind of the dominant one, especially from late spring to early fall. And then you get a lot of mild and modified Pacific air masses coming into the Great Plains and the Great Lakes, or modified Arctic or continental, excuse me, maritime polar air masses coming in to the West Coast. So these are the areas of the country or of the continent that have the most dominant air masses. The air masses aren't static, though. Of course, they're moving around, so they do modify. There are changes in humidity and temperature and the stability of the air masses. Remember, by stability, we mean how the temperature changes vertically. If something is warm above, cold below, that's very stable. Because if you try to move air upward into a layer of air that is warmer, that air kind of returns down toward the ground. The flip side is true as well. If something is unstable, if it's very, very cold over top of something that's warm, that warm air rises into a much colder air and goes flying up like a hot air balloon. Okay? That can change during the process of an air mass modification as well, either through radiational effects, vertical motions, or as it moves over a different source region. That air mass starts over, let's say, central Canada, and then works its way down to the southeast United States. It kind of transfers. Same thing, taking a maritime polar air mass over the North Pacific, and then you rain it out, if you will, as it crosses the Cascades, and you have a much more modified Pacific air mass. It's not truly maritime. Wouldn't go as far as calling it continental, because, although there are 4 basic classes of these air masses, you can't put them all in a convenient bucket. There's a little bit of wiggle room in between all of them. So let's get to fronts. You've probably at least heard of fronts, cold fronts, warm fronts, stationary fronts since you were a kid. So what are fronts? All right, fronts are basically where the action is regarding weather. The concept of a front came around about 100 years ago, again from the Norwegian Cyclone Model. Jakob Bjerknes and his colleagues about 100 years ago came up with this model that we still use today. And it's a conceptual model. It's not a numerical model, but it's a conceptual model of understanding how things are moving in the atmosphere. And they use the term fronts because this was developed in World War I. And of course, World War I was a great war. Fronts were where the action is, and that's why they gave the name fronts to these places where air masses are coming into contrast with one another. So a front is a narrow zone of transition between these air masses, and they're going to differ in density because temperature and humidity are both tied in to density. And you name the fronts depending on which way the cold air and warm air are moving. A warm front means your warm air is advancing and your cold air is retreating. Cold front's the opposite. Cold air is advancing and the warm air is retreating. Frontogenesis, genesis meaning you're creating something. That's where your front is forming or growing stronger. Frontalysis, which almost nobody ever uses this term, although it is a fully acceptable term. That's where the fronts are weakening or starting to wash away. So let's start with the warm front. You've got cold air. Again, cold air is more dense. All right, think about that stuff that came into the southern plains all the way to Texas back in February. It just kind of oozes down the center of the country in between 2 mountain ranges, in between the Rockies and the Appalachians. All right, so that cold, more dense air retreats and the relatively warm air advances. And the temperatures here are relevant. You can have a warm front where you're bringing in 45 or 50 degree air if your cold air is 15 or 20 degrees. All right, so cold and warm are relative to each other. In this situation, the slope of the frontal surface is less, and I'll show you what that means in the schematic. But this generally is associated with broader area of clouds and precipitation. You'll hear this called overrunning. overrunning precipitation or gliding or something like that. Effectively, you've got warm air running over top of cold air. So it looks this way. If you look toward the bottom right there, you see the red line with the semicircles, the red semicircles. That's the direction in which the warm air is heading. So if you look at that bottom rectangle, the red arrows where it says warm, moving basically to the north. In this particular diagram, north is to the left. So the air at the ground on the south side, or in this case, the right side of the front, is from the south, and the front is pushing northward. All right. But on the left side of those semicircles, you see the arrows kind of pointing down into the left. That's actually suggesting that the wind is from the east. Think about the classic compass direction. If I've got winds from the south on the south side of that front, on the north side, they are generally from the east, sometimes slightly north of east. That's just at the ground level. As you go farther up, you see 5, 10 kilometers by the scale there on the left side of the page. And then those other arrows with the white clouds showing you that the air aloft is moving up this kind of wedge-shaped thing, or that's why we call it overrunning. Your warm air is overrunning or running over the relatively cold air beneath it. So as that air moves northward over top of that cold air, you start to get condensation and you start to get cloud cover. All right, so very close to that boundary where the warm front actually is, you're going to have a lot thicker cloud cover and generally steadier and relatively heavier precipitation. But farther ahead of that, in this case much farther north, you still have a tiny bit of overrunning, but it's so high up into the atmosphere at that point, 25, 30,000 feet sometimes. All you have is a few ice crystals starting to form in your clouds. Those are the cirrus clouds, which you see at the far left part of that diagram, the CI, the cirrus clouds. So the cloud types change as you go farther to the south toward the front and obviously farther down in the atmosphere. Some cirrus clouds to the top, cirrostratus, altostratus, nimbostratus, and ultimately just low-grade stratus clouds. The cold front is where we see some of the strongest or sometimes truly severe weather, and by severe we mean damaging kind of weather, severe local storms. This is where the colder and more dense air displaces the warmer and less dense air. The warmer air is lighter, so the cold air kind of rams into it, just kind of punches into the warmer air, and the air goes up a lot more rapidly versus that glide that we see in a warm front. So the temperature and the humidity drop substantially and rapidly after the passage of a cold front. So the slope of this cold front is a lot steeper than the slope of a warm front. And that kind of looks this way. The same directions apply here. Okay, in this case, if you look at the bottom right, there's the line with the blue triangles. That's the cold front and the direction of the cold front. So this cold front is coming from north to the south. And immediately behind that, or to the north, you see those red lines kind of pointing toward the cold frontal surface itself at the ground. And those are lines of constant pressure, P1, P2, P3, P4. All right. So you see a little V shape in those lines and those pressure lines. That's a surface trough or a little area of relatively lower pressure. It's not a circle of lower pressure, but it's relatively lower pressure. And that's where we will see the cold fronts normally kind of setting up, or what they kind of fit into. So in this case, you see the cold air advancing in that kind of wedge situation from north to south. South side of that front, we've got a wind more from the west, but can just as easily be from the southwest. But then aloft, everything is just coming from the north or northwest. So you've got this big wedge of dense cold air. You think of it like oil and water, just ramming into this warm air, forcing it up. That's what the CB and CI are, the clouds, cumulonimbus and cirrus clouds. All right. So that forces air up very rapidly over a shorter distance. So you're going to get more intense cloud cover, more intense precipitation over a shorter horizontal distance. All right. So the warm front, you've got a broader area of precipitation, tends not to be as heavy, longer distance. In the cold front, again, the cold air smashes into the warm air, forces the warm air up. You get cloud development and heavier precipitation over a shorter distance. Those are some of the key differences between the two fronts and the weather that comes with them. Stationary front, as you might guess, just means front's not moving. Doesn't have a lot of forward movement. Reason for this is that the steering winds or the jet stream winds, which we'll get to in a minute, are largely parallel to the front. So we don't see the cold air advancing or retreating. We don't see the warm air advancing or retreating. This can also happen along a boundary between the land and the ocean, especially during the wintertime when you've got colder land and a relatively warmer ocean. Let's say you've got 20-25 degree air over land bumping up against a 50 or 55 degree ocean. That'll give you a heck of a front, even though it may not move. So the schematic on this looks a little bit different. It's not as active. This is where you end up getting a lot of low clouds, lighter precipitation. Sometimes you get the drizzle, and it just kind of hangs for a day or two before something comes along and kicks this thing out of the way. And by that I mean some kind of shift in the jet stream flow, which will ultimately turn this into a warm front or a cold front. But for a while, if it doesn't move, it's just stationary. So at the ground level there, again, we've got the same conventions as before. The stationary front, you've got the cold air to the north, the warm air to the south. You've got the triangles and the semicircle there kind of showing which way is which. So the air at the ground doesn't necessarily push the warm air or cool air one way or the other. They're kind of parallel to the actual frontal surface. So you've got winds to the south of the front from the west. You've got winds to the north of the front to the east at the ground level. But you still have a little bit of upglide, if you will, farther up into the atmosphere, several kilometers up in the atmosphere. So you still get a fair bit of cloud cover. And where you have these close to the east coast, which is where most of us live, and you have that east wind coming off the Atlantic, that's part of the reason we get so much cloud cover. But in time, stationary fronts will either wash out or something will come along at the jet stream flow and kick the winds aloft in enough of a direction to move it. An occluded front it's not something that's very intuitive. It's late in the life of an extratropical cyclone or big area of low pressure. It depends on the characteristics of the air behind the cold front and then ahead of the warm front. There are cold occlusions, warm occlusions, neutral occlusions. Most of what we run into here in the eastern U.S. is a cold occlusion. And it kind of looks like this if we look at it from the side. The cold type occlusion on the right, which is the one we think of the most, is when you've got a cold front catching up to a warm front. So what do we mean by an extratropical cyclone? It's basically an area of low pressure that isn't a hurricane. You know, we think about these large areas of low pressure. Any area of low pressure is a cyclone. Any area of spinning low pressure is a cyclone. The extratropical cyclones are these big areas of low pressure that we think of as winter storms, rainstorms, those kinds of things. So to be specific, they're synoptic scale, large scale, make up the size of a state or a couple of states that occur in the middle part of the latitudes, mid-latitudes, let's say between about, 25 degrees north, 60 degrees north, and form along a cold front or the polar front. And by polar front, we mean the main boundary between colder air to the north and the relatively warmer air to the south. You oftentimes see them shown in satellite imagery as a comma cloud. They are non-tropical, which means they're cold core. They're getting their energy from the lateral changes in temperature over a horizontal distance. Tropical systems, which we'll talk about, get all their energy from warm ocean water. All right, we'll get more to that. But again, this is the classic Norwegian cyclone model that was developed about 100 years ago. To get these areas of low pressure to form, you're going to need some kind of support in the middle and upper levels of the atmosphere. Effectively, you will have the jet stream kind of wobbling along, and if that little wobble comes across an area of temperature contrast in the horizontal, you begin to develop some upward motion and you begin to develop a circulation. What does that look like? All right, kind of like this. Look at the top one. That's looking down from above. And there we're looking at the jet stream flow. You've got the ridge, trough, ridge, right? As the air moves through those lines, that's the gradient wind. The wind slows down in that left part of the screen. As it goes toward this trough, it has to effectively slow down and make the curve, if you will. And then as it comes out of that curve, if you will, it effectively speeds up. So there's a divergence. We talked about convergence and divergence a few lectures ago. So the wind slows down as it approaches the trough. That's convergence. So if the wind is slowing down aloft and converging, that means there's going to be a buildup of mass, which means there's going to be a sinking. And that's what you kind of see there in that middle schematic, the subsidence and the convergence and subsidence. So air is building up and it starts to sink. And as the air sinks, gets down toward the ground level and spreads out, that's an area of high pressure. You have divergence, so air hitting the ground, diverging in all directions. Okay? And the opposite side is true. You're coming out of that trough, and again, this is jet stream level, gradient wind. It accelerates coming out of that trough. It's made the curve and it starts accelerating. So the wind speeds up and there's divergence. Right? So if you've got divergence, 15, 20,000 feet up in the sky, you got air moving faster as it moves along in the horizontal direction. That's going to lead to some ascent. The air has to come in someplace to take its place. All right? So if that air is rising, that means down toward the ground, air is going to have to come in to take its place. And because we do live on a rotating sphere, as air moves up and air rushes in to take its place, it rushes in from several directions on a spinning globe. So you're going to develop a spinning area of low pressure. And that's what the con is down there at the bottom right, convergence. So when that happens, over top of an area close to the ground level where you have a temperature contrast, horizontally, that's going to start to develop an extratropical cyclone. So the support comes from the jet stream level. And the jet stream is a term that gets tossed around a lot, but it is a relatively narrow maximum in the steering winds, 15, 20, 25,000 feet up in the sky. The wind is blowing at that level all the time, but that area where the wind is blowing the fastest, that kind of ribbon of strongest air, is what we refer to as the jet stream. And most prominent is the one is along the polar front. Now, embedded within the jet stream are little areas where the wind is faster than others. That's called a jet streak. So that's an area where the winds are strongest within that ribbon of strong air. And within that ribbon, you have additional areas of convergence and divergence, again, 15, 20, 25,000 feet up in the sky. And this will provide additional support for the cyclone by getting a little extra lift, if you will, in the divergence aloft. And from the schematic there on the bottom, you see where that jet streak plays out, where the circles there, these ovals, are isotax lines of constant wind speed, 140, 160, 180. So you have a localized maximum in that wind speed through the jet stream. All right. So coming out of that, just to the left front is an extra level of divergence, and to the bottom front, right front in this case, not really bottom, but right front, is convergence, and it flips on the other side. During the course of the year, there is seasonal change in the mean or average position of the jet stream, or the polar jet, if you will. And this starts to make intuitive sense if you think about the temperatures in the summer and the temperatures in the winter. It's colder here in the winter, no shock. So as a result, the average position of the winter jet, the polar jet, is going to be farther to the south. During the summer, as most of the continent heats up, the cold polar air retreats back toward the pole into Canada. So the mean or average position of the jet stream is farther to the north. All right, so the mean average position of the jet stream in the winter is farther south. During the summertime, the continent heats up, so the coldest of the air retreats toward the pole, so the average position of the jet stream is farther to the north. When we think about the life cycle of an extratropical cyclone, we have to think about the polar front. We have to think about where those temperature contrasts of the ground set up. All right, so as the surface pressure drops and the winds respond to that, again, like I said before, pressure drops, air spins around to take place, and everything moves upward. You begin to see frontal features developing and air begin to move farther. I mean, it's not a perfect circle and going up, because you've got friction, you've got land masses in different shapes and configurations, okay? But it kind of sets up like this. And let's walk through this top to bottom. You've got some kind of temperature contrast from northwest to southeast there, all right? Then you get a buckle in the jet stream, because the jet stream always moves in waves like water through a stream, all right? There are always these ups and downs, waves, ridges, troughs, that kind of thing. So when a trough moves over an area where you've got a pretty good temperature contrast to start off with, you begin to develop a different kind of wind flow around that area. So in that first frame, the jet stream winds shown there in the dashed lines move over that area of temperature contrast and start to develop an area of low pressure. All right. Once that happens, the winds at the ground, at the surface, start to react to that. While that is going on, you probably have, or you're going to have, some kind of deepening of the trough higher up into the atmosphere. Again, 15, 20,000 feet. So you start to see the trough in the second frame there, B, a little sharper. It's a little more defined down to the south there, the dash lines. So with that in mind, your cold front begins to advance from A to B there. Your warm air doesn't move quite as far to the north. It hardly moves at all sometimes. Your cold air, because it is denser, is driving the system far more than the warm air. Because warm air is relatively light and relatively less dense, it basically has to obey what the cold air is doing. The cold air is what is driving this feature. So the cold air advances, and then it starts to spin around the area of low pressure. And that's what you see there in the third frame. You see the L, and then you see an occlusion starting to take place, that occluded front, that little place where for the center of low pressure to where the cold and warm front begin to split. And that goes on even further as the cold air begins to wrap all the way around the extratropical cyclone. And that's a time when you start to see the cyclone begin to decay, because you've started to lose those temperature contrasts around the circulation. All right, so that's where you've got that big occluded front, which is that purple area where the semicircles and the triangles are on the same side of the boundary. So you've got the wave of low pressure, you've got the cold air advancing, and to the point where the cold air catches up to the warm air near the center of the storm, the center of the cyclone. The storm occludes. Again, the cold air catches up with the warm air. So when that happens, you lose your temperature contrasts and your storm begins to weaken. The cyclone begins to weaken and ultimately just die. And that's what it kind of looks like at the end of its life cycle from the satellite imagery. Cyclolysis, which is a word nobody ever says, but yes, it is a word. So yeah, that point where the occlusion happens is known as the triple point, and that's the beginning stages of the cyclone starting to die. There are some specific parts of North America that are more favored for these storms to develop. Preferred regions, if you will, of cyclogenesis. They tend to be nearby sources of warm, humid air where they interact with areas that are cold and dry, so you get a bigger temperature gradient. And also in areas on the lee side of mountain ranges, because you're going to get areas where there is more warming. You're going to get a decrease in stability as warm air comes over top of the mountains. And that kind of looks like this. Those areas in orange tend to be areas where we have preferred cyclogenesis. And for our purposes, it's mostly there in Colorado, Gulf Coast, and the Atlantic coast. In Gulf and Atlantic coast, because you tend to have warmer water next to colder land, because you tend to have these cyclones more prevalent in the spring, fall, and winter. And then lee cyclogenesis. The air comes over the mountains, descends, it warms, it actually stretches a little bit because you've got a narrow ribbon of air coming across the mountains, descending and kind of stretching. And those contribute to a little bit of spin into the atmosphere. So between that and the warming of the air, that gives you a drop in pressure. And that will help to generate a cyclone, or at least get one started. So those are the areas that are most favored for cyclogenesis. And these are the two main reasons. Again, the air stretches and warms on the lee side of a mountain, and then large winter temperature gradients are found between the land and the ocean. Okay, and that's it for this one. Not quite as long as of a lecture, but really you need to walk out here understanding the fundamentals of the Norwegian Cyclone Model. That's what this is kind of all about, understanding that. So the weather looks like this. Based on the surface weather, you get a mature cyclone that can be divided into 4 sections: northwest, southwest, northeast, and southeast. It looks this way. There's your area of low pressure. The cold front advancing, the warm front advancing, or advancing more slowly. So you've got fog, rain, drizzle, snow, rain, thunder showers, all kind of favored in different parts of that feature of the cyclone. You've got a steadier rain to the north and northeast side. You've got heavier rain, thunderstorms right along the cold front. And then back in what's called the cold conveyor belt, back to the central and northwestern part of the cyclone, you oftentimes have the coldest precipitation. That's where the snow is most likely. And very close to the warm frontal band itself is where you'll have the low clouds, drizzle, and fog. So that is a good schematic to keep in the back of your mind. So with that, we'll close. Next time we'll do air and sea interactions, talk a little bit more about how the air and water intermingle, how they drive weather, how they drive climate as well. So we'll see you next time.